Hey, I'm Derek Vargare, Vanguard Audio Labs. I'm here down in Mountain View, Arkansas with Matt Anderson at Mill
Hello.
Sound Studio. Your incredible studio out here that, as you can see behind us, has some really awesome gear, get great sounds out of here. And we've decided to make our, what would you call it, our final tweaks or part of the process of the tweaking for the V14.
Yeah, like you usually say, a small snapshot of the final tweaking stage because I know from the past, I've got to compare a solid state version of your mic that's transformerless to like a tube version with a transformer and kind of see, how does a tube mic versus a FET mic compare when they've got
Mhm.
same capsule and similar circuitry. But in this case, we're getting a lot more specific and looking at, you know, switching out some components like caps and stuff because we've already heard your V24 and you've got that design hacked out and sounding good. And in this case, you've got more physical room in the mic and stuff, so you can try a bunch of stuff that you couldn't try before because of things like physical space constraints and stuff.
Yeah. Designing in a microphone is this three-dimensional equation, and having one mic circuit in the body instead of two certainly makes things much easier. Also, what makes it easier is the C24 is, if half of the C24 is self-biased single triode design, and because of that, there's very few components in there, so I can really playing with one component in the signal path can make a pretty big difference because there's just
Sure.
not that many between the capsule and the output. So I'm really looking forward to seeing what we can do. I brought a bunch of components here that we can change out, different capacitors, tubes, things like that, to try and decide what's better.
And
And
like the plate voltage thing, that's going to be new.
yeah, that's the plate sag voltage. That's the primary reason we're here. We're trying to figure out if this is going to be a useful thing for engineers, but being able to,
Seems good in theory, but we have to actually try it and see if it's going to be useful.
yeah, yeah, absolutely. I certainly, I'm excited because I don't think it's ever been done on a microphone before, and I'm about originality. This is, a lot of people think about clone microphones and trying to sound more like the original designs or the original designer's intent on the original designs. And I'm taking the circuit, and I'm certainly using an authentic capsule. Thank you, Ben at Bee's Knees. But I'm definitely not trying to make it sound like a C12.
Sure.
I'm trying to make it sound as interesting and as useful as possible, and give you a new color on the palette as opposed to a different shade of the same color that's been iterated again and again. So this is just a snapshot of that iterative design process where we're doing a couple changes. I think we've got 5 or 6 planned. Actually, we have a big list, but I don't know how
Got
many
to
of them
narrow
we'll
it
get through.
down.
Yeah. And we're just going to see which ones make a big difference, what we like. And it's nice because it'll compound on itself. If you get a mic 5% better, and then 5% better, and then 5% better with 3 tweaks, you've got 15% better. But
Right.
arguably, you've got more than that because it's like compounding interest. And that sort of continuous improvement is what takes a mic, I think, from a pretty good mic coming out of the lab, so to speak, with objective measurements, to a really useful sonic tool that gives you a pleasing sound. And that's the subjective part of mic design that I think is the much harder part, because it's kind of there's endless combinations and you can tweak forever. It's kind of like making an
Sure.
album where you're like, eventually you got to release the dang thing.
We're done now.
Yeah, exactly. And I think the second part of it is it's not an exact science. You just kind of have to listen. And sometimes the thing that costs $1 sounds better than the thing that costs $50.
Yep.
And so it's about going in with an open mind and not having a bias towards more expensive things. But it's nice to have the room in the budget with more expensive microphones to use more expensive
At the
things.
very least, try not to blow anything up. It's
I can't promise that.
just how it goes
Yeah,
sometimes.
yeah. Well, trial and error, heavy on the air.
But I'm really excited to do this because I don't have the knowledge base to make a mic. A little bit of knowledge is dangerous. So I've got some preconceived notions of what I think is going to happen, but I've never had someone bring mics in and start switching out individual caps and stuff in it. So I mean, like Derek said, it's a more simple circuit. So some of these things could make, in theory, a big difference. We don't know yet. And even if there are audible difference, you get into subjective. Is this better? Do I just like this better?
Yeah.
Are
and is
we
it
going
better
to
for a certain
disagree?
source?
Yeah, exactly.
Yeah. Yeah. So on that note, let's get tweaking.
Yeah, let's do it.
Let's go. So one thing that people like to do in their mics, and one thing I like to do personally in my mics, is swap the tubes out. It's one of the easiest modifications you can make, as long as the tube is socketed, that can really change the character of a microphone. So I've got 2 mics on the table here, and we'll go over some tube swapping tips. One thing that's cool is you can swap just between brands. Like here's a vintage tube versus its modern, currently manufactured counterpart. And both of these tubes, even though they're technically the same spec, will sound very different from each other. And so you can get different audio characteristics that way. The other thing you can do is you can actually swap tube models. So if I went from a 12AY7 to a 12AT7, I am putting a tube in that wasn't designed for that particular circuit. As long as the pinouts are the same, it will still function, but it's going to alter the way the circuit operates. Objectively, the circuit will perform poorer, but it might sound more musical, and subjectively, that's really what matters. So I'm going to pivot over here and kind of show you some basic tube swap tips and jiggle around the table with my foot while I'm doing it. So we got 2 GE 5-star 6072s in here. Very difficult to get your hands on these days to get mic grade ones. I am going to go ahead and pull one of these out. So as I'm doing this, you'll notice that I brace this circuit board. It's really important because otherwise I'm torquing it and I could tear the pads off of the PCB behind it. I'm going to just gently walk this out like I'm moving a heavy piece of furniture. I'm just wiggling it back and forth and putting backwards pressure. And this tube socket is a little bit tight. You can actually use just a flathead screwdriver to either push in between the pins incrementally to give them a little more room, or if you bent them too far out, you can bend them back. You don't want to do it too much, or you could break them, but that is a good way if you've got a really, really tight tube socket to get the tubes back to where you want them to sit as far as pressure goes. So I'm going to put an Electro Harmonics modern 6072 next to this vintage General Electric one. General Electric. The Human Torch was denied a bank loan. And we're going to see how these 2 tubes differ from each other. I don't expect the sag function to do much with it because they are the same, but I'm curious if we keep them both at optimal voltage, what our audio changes is. So let's find out. One thing that you're going to notice as soon as we pan over to start the acoustic guitar test is that the microphones are much further back from the guitar than you typically would mic an acoustic guitar. There's a really simple reason for this. It's all about angles. So if right now the capsules are separated, the center of the capsules are separated by maybe 1.5 inches, 2 inches. And if we were to move those closer to the guitar, then that distance between the capsules becomes more exaggerated. And what we're trying to hear is the changes that we made in the mic, not a slight distance in placement. So when we move them 2-3 feet back from the guitar, then that difference in placement pretty much doesn't matter, and it's all about the changes that we made. So it's just important to note that we're not trying to get this guitar to sound really good in these tests. We're more trying to hear the changes that we made in a more objective fashion. So that was a swap of different makes of the same model. And now what I've done is I've actually borrowed Matt's V13 tube. Thank you very much, Matt. And we popped the V13 tube in the V14. And we are going to see how this guy sounds on guitar as well. Now, this is a model change. So this circuit was not necessarily tweaked and designed with this tube in mind. So it's not going to operate objectively at full capacity, but that's not what we want. We want musicality. So the first experiment that we're doing right now is we're experimenting with starving and pushing the plate of the tube inside the V14. And the reason that we're doing that it'll be a useful tool for an engineer or a producer or a musician, is it's going to change the harmonic distortion characteristics of the tube. Now, the other thing it will do necessarily, because this is a single gain stage design, it's only using one triode in the vacuum tube, is it's going to change the output level to a degree as well. When you get really low on the voltage, it's going to reduce the output level quite a bit. And if you get too low on the voltage, the tube just shuts off. It can't work without enough voltage on the plate. And you're going to get a lot of second order harmonic distortion as you turn it down. And then you're going to get third order harmonic distortion and less second order as you turn it up. And as you turn it up, we're probably looking at gaining 4 or 5 decibels of output. And as we turn it down, we want to find a sweet spot where I've got this pot probably going from 0 to like 110 volts, but 0 is a bad place for the pot to end. We want it to end probably somewhere in the neighborhood of 20 to 30 volts, and we're going to find where that sweet spot is. And then we'll wire up either a 3-way switch or a 9-way switch, a resistive ladder on the final product, and it'll tell you, here's how much gain you're losing or gaining on each one so you can compensate in your DAW. So this is a modified V13 power supply that I've kind of kludged a potentiometer into, and we're going to go ahead and wire it up so that it will give us that voltage range that we're looking for on the load line of the plate. So you can see this is a V13 power supply. It even says it right here, V13 Gen 2 PSU PCB version 3.0.2. Okay, so what we've got is I just got to wire up this potentiometer. I've got my little field modification kit here at Mill Sound Studio. I'm not in the full office. I don't have all my really fancy tools, but you don't need fancy tools to make this work. So we just got to get these 3 wires. I've already got them tinned and stripped and wired into the proper places. This is just my ground wire here, which is dumping the voltage, this black one that I've inserted in, dumping the voltage into ground. I just realized I don't want to desolder and resolder this for every take, so we're only getting 1 take. I better not mess this up, huh, Matt? So, and then here's the actual feed wire that's going to feed one of the pins on our 7-pin cable and eventually feed that tube plate. And it is sitting between the ends of the resistive strip on the potentiometer, and that's what's giving us our voltage. We're basically just wiring up a voltage divider for you electronics geeks. It just has to be, oh, I didn't quite get that one where I wanted it to be. There we go. Let's try that again. Let's just get it in place, and then once it's in place, I'll add a little more solder there. All right. Now that it's flowed, I can probably just add it right from the iron and not worry about flux too much. There we go. Hold it still. Let it cool. There we go. We got a good solid connection there. But yeah, it's basically just a voltage divider, and the pot is a sufficient value to where it's gonna operate when it's at the ideal operating point of the V14 tube. We want it to act like this pot isn't even there, that the series resistance of this side of the pot and the resistor that's in the V14 add up to as if we were using the original value. So that's some serious nerd stuff that's probably not important to a lot of you, and you don't really care about. But the bottom line is, now I'm going to go ahead and test this voltage here, and we are going to see if this if I wire this up correctly. So in theory, when I turn it left, the voltage should drop to 0. When I turn it right, it should go up to, right now it's not connected to the mic, so I think it's going to go up to around 140 volts. But I'm going to get a little kind of test pin. I'm going to cut a little bit of solder here that we can just use to check the voltage coming out of pin 4 and make sure that it's all working good. So I'm just going to take this, don't try this at home, kids, and stick it in pin 4. Make sure it's not touching ground. I've got my multimeter set to DC voltage. We're going to find a nice little ground point that is convenient to clip onto. Here's one. You're going to see the top of my head mostly in that shot, and that is what it is. Then I'm going to clip on to that pin 4 voltage. We're going to start it at, in theory, full voltage and make sure I haven't wired this backwards, which I really have a penchant for wiring things backwards. So we've got it plugged in. The switch on this is actually upside down, so it's not on yet. That's okay. That's why it's a prototype and not the final unit. Remember what I said about wiring things backwards in the past? Fortunately, if you look here, it looks like we are getting full voltage. We're getting 130, probably going to come up as it warms up to 138 to 140 volts, which is exactly what we're looking for. And then as I turn this knob down, you're going to see that voltage drop. And I would love if it's idling right in the middle at about 65 volts, but that's probably not what's going to happen because we haven't found that sweet spot yet. Here's the middle, and you can see we're running around 80 volts, which is just a little too hot for my liking. And then you can see me drop it all the way down to essentially 0 volts. We've got 1 millivolt sitting on the plate, which isn't going to do anything for that tube. So yeah, it totally works. Let's close it up and let's see if this is doing what we want it to do. So what we're doing here is we're running a 1K test tone. You can see the 1K, and you can also see the 2K total harmonic distortion. You can see the harmonic distortion, the overtone there. And what we're doing now is we're going to push that voltage all the way up. So we're getting way more clean headroom. And now that harmonic distortion is much, much lower. And then as we start to back this back down and we get back to noon, you can see that second order harmonic coming back up. And then we're going to keep going down and they're getting closer and closer to each other. That is the total harmonic distortion increasing and increasing. And what we're trying to do here is find a sweet spot, right? We've lost about 30 decibels of gain at that point. That's really not a usable microphone. So we're trying to find the spot where you've got a lot of THD and you're getting interesting saturation, but you're not losing so much signal that it becomes unusable. And it's probably right about there. That's a really good spot for it. And as we come up, you can just see that relationship between the second order harmonic and the first tone really change. And now we're back at noon. So one thing I tend to experiment with whenever I am designing microphones is capacitor choice in the coupling, or the decoupling rather, between different parts of the circuit. Those are in the signal path and they tend to impart their own personalities on the audio as it passes through. It'd be nice in theory if every component was theoretically perfect, but that's not the way components work. And so you can change the value, you can change the series, you can change the manufacturer, and you get slight changes in the sonic response of the microphone and its fingerprint. And when you add those changes up, if you're changing 2% here and 2% here, it's not long before you have 20 or 30 or 40% changes with just really small changes in the microphone circuit. So what we've got in these two here is it got a 1.5 microfarad, which is the original designated circuit value in like a C24 in the standard mic. And then in this one, we've actually upgraded it to a 2.2 microfarad. And that value change is going to change where the roll-off point on the bottom end of the circuit is. And believe it or not, even though it's technically out of our audible range, it does affect things within the audible range. So these are Solen capacitors. These are Solen fast caps. My dear friend and mentor Ken was the first person I know that put one in a commercial microphone. He kind of discovered them through his love of hi-fi stuff. And really, they just sound so darn good. Don't underestimate, or I would be careful about classifying components by cost and always do blind testing, which is what we're going to do with these tests, because you just don't know what's going to sound good to your ears and what's going to sound good in that particular microphone circuit, whether or not it's $1 or it's $100. So these are fairly inexpensive capacitors compared to this guy over here, which is probably like a $20, $30 capacitor, but they sound really, really good. I have yet to find anything in that price range that beats them out, and even in higher price ranges. So don't judge a book by its, I guess not cover, but maybe price tag in this particular case. We're gonna see how these sound, and we're gonna do it blind, so you can decide which one you like better. We heard how the two Solen fast caps sound against each other with different values. Now we've changed to actually the same value, 1.5 microfarads on each, but it's a different brand, it's a different style. I think the dielectric's even a little different. And all these things change the sound of a capacitor. Now, a couple things I want to note about this is, first, when you design microphones, you have to think a lot in 3 dimensions. If you notice, if you look down the middle here, all of my tall components, the transformer, these two electrolytics, are in the middle of the microphone PCB. And the reason is this is an arch, right? So as this goes over the top, my clearance on the left and right sides of the PCB is not going to be as tall as my clearance in the middle. So you have to think in 3 dimensions a lot when you're designing microphones. The other thing is component size. A lot of times I would like bigger and better components in my microphones, and there's just no way to accomplish it without making the microphone itself physically bigger. For instance, there's film and foil capacitors, Teflon capacitors that might sound way better in microphones sometimes, and I simply wouldn't know in a lot of cases because they're too large to fit in the microphone body along with all the other components. So it's actually a really interesting choice limiter when it comes to microphone design because you can only fit certain things in the mic to begin with. So we're going to go ahead and test the 1.5 microfarad caps against each other, and we'll see how it sounds. At this point, Matt and I have listened to some of the capacitors that I brought, and I feel like we made a pretty good choice with the capacitor that we chose to put in, which is the Solen 2.2 fast cap. The differences between it and the Auricap are surprisingly subtle, and we think that it's pretty shocking that $20, $30 capacitor and $2 capacitor could be that close to each other. And I felt like the Solen had a little bit more top end. It was the Auricap kind of felt a little scoopy to me. And so we decided to go with the Solen. So I've actually soldered it into this, and we're going to change the other mics, and then we're going to move on to the next decision. Now that we've made the transformer decoupling cap decision, we've actually put something on the PCB that might be useful to mic geeks. And for me personally, I put it on the PCB because I wanted to play with it in the prototypes. So you'll see here, there's CX on each PCB. And I've actually got some notes on there on the recommendations for values. But what this does, this is a bypass of this capacitor here. So you put them in parallel. It doesn't really change the value, but bigger caps, this is an oversimplification. Bigger caps, you tend to, I would argue, lose some high frequency fidelity, particularly with electrolytic capacitors. So when you put a bypass cap that is much better at dealing with those high frequencies, then you are actually creating an alternate path. You're not really altering the value of this capacitor in any meaningful way because capacitors in parallel are additive, but you are creating an alternate path, and you can actually add some of that high end back. Some high end microphones actually are just a cheap electrolytic capacitor with a bypass cap across it that's a higher end capacitor. So we're going to give this a shot. We're going to see how much of a difference it makes. I'm kind of curious. All right, after that test, Matt and I both decided that we actually like the bypass cap on this particular microphone. We found it to be pretty subtle. I would say pretty subtle. But you can see the bypass cap right here that we've soldered in. And it definitely adds a little bit more clarity, I think, is what we kind of both agreed. It adds more clarity. It's not making it brighter, just sounds a little less, what's the word you would use, Matt?
Phasey, maybe?
Maybe phasey. I don't know. It certainly sounds a little more hi-fi, and I think that's the ultimate goal, is we want this mic to sound as clear as possible. So on to the next thing. We made a couple mods to the original plan at this point, kind of the baseline mic that I had created. And I'm pretty happy with those modifications so far. I think we've really come up with something that sounds pretty darn good. Now, the next thing that we want to try is the cathode bypass cap, whether it's the value or the brand of manufacturer as well as the series. These do make a fair difference in the response of the mic. I think the biggest single thing you can do is increase the value a fair bit. A lot of companies tend to jack it up, I think, too high. And we also have a bypass cap across the cathode bypass cap, which sounds a little confusing. But what we're going to do right now is we're going to sub out this brand that's no longer manufactured, the Elna Mic 2, but I have plenty of them at the shop, with this Nichicon Muse, and we're going to see what sort of difference we create. One thing we did on the V24 that was pretty useful was a voicing switch. And the voicing switch, the idea behind it is the original AKG C12 versus the Telefunken 251, which were both made by AKG. One was just made for Telefunken by AKG. One of the biggest differences that people talk about between them is the top end. The C12 tends to be a brighter mic, whereas the 251 has a smoother top end. And we created a voicing switch on the microphone on the V24 where each of them were independently switchable between like a 251 mode with a subtler top end roll off and a C12 with a brighter top end. So now what we've done is I've expanded upon that with a three-way switch because I have room on the PCB. And am I not going to use that? I'm definitely going to use that. So there's three modes. This is in the middle. We've got the C12 mode, a brighter top end. Then we have a very subtle roll off on the top end for the 251 mode. Kind of puts it in the Goldilocks zone. It's honestly my favorite top end of any microphone is that 251 top end. And finally, on the inside, we have, I'm kind of calling it ribbon mode right now for lack of a better term, but it's a much stronger, darker sound in that voicing. So at this point, we've made 3 decisions that have actually changed the original unit that I brought in. I want to reiterate that this is a snapshot of the process. It took us 2 days to make 3 decisions, so you can kind of get an idea of how long this sort of things take. You have to do sanity checks at times and put 2 mics that are exactly the same next to each other to make sure that your ears are working right, that there's not a placement issue, or that something hasn't been biffed with all the soldering and desoldering. So it takes quite a bit of time just to make sure that everything is kosher and that you're happy with it. So, once again, it's a snapshot of part of the process, and the process is going to keep going. I have to make adjustments to the design based on the changes that we've chosen to make. So at this point, what we're going to do is Matt is going to play guitar again, and we have one mic where the 3 component changes that we made are going to be present, and we have one mic that's going to be the stock mic that I brought in that I thought sounded pretty good, and the objectives checked out, the noise floor and things like that. But then you get to the point where it needs to come into the real world. And so we're going to take a listen to these, and then you're going to also hear them in a more realistic miking setting, because right now we've got them pretty far back off the guitar. This is not how you generally mic an acoustic guitar. So we're going to get them in more realistic studio situations to see how they stack up.